But we can form bromine radicals by the homolytic cleavage of the bromine, and the bromine radical will strip an H out of the alkane, making HBr and leaving behind a radical. Where are we going to leave a radical at on the alkane? At the best side. What's the best side for a radical? Tertiary, just like a carbocation. And radicals can also be stabilized by resonance like carbocation. And that's why we tend to have regioselectivity, because most stable radicals are going to be formed in the alkane. We did the mechanism. We can compare that to alkene, which is an ionic mechanism, bromonium ion. We do an addition reaction here. That's the old alkene reaction. You did that in lab. Remember, one hand behind your back? Where the above reaction is a substitution reaction. Because bromine is replacing one H. No H is replaced down here. We're just adding two bromines. We did mechanism. Okay, let's see if we can predict products. What did you get for the first reaction? Can you name your product? Anybody got a product? Can you name it? Yes, 1-bromo, 1-methyl cyclohexane. Bromo, 1-methyl cyclohexane, of course, plus HBr, yeah, that's a small molecule side product. Yeah? Mechanistically, light's going to cleave this, bromine radicals. Which H is going to be abstracted? Again, we're going to take this H here. Mechanism we did, we're just focusing on this site because we make a tertiary radical. And then the tertiary radical reacts with bromine to brominate and reform bromine radical, which is propagation. And the bromine radical can come back and strip another H out. And then you have a cycle, right? Yes. And we can make that compound there. How about this next one? We got bromine. This is benzoyl peroxide. If you look at that, it is O2. Okay, it's O2, and each oxygen has a benzoyl group. Benzoyl is a phenylcarbonyl. That's what that is, shown condensed. Okay? It's a peroxide. These are benzoyl groups. We'll look at such in organic too. When we do carbonyl chemistry, acid derivative chemistry. So it's benzoyl peroxide. You can also have, of course, the peroxide is when you have the OO bond. Okay? You can also have H's there, and that's called what? Hydrogen peroxide. Okay? In your medicine cabinet. But it's not organic and it's aqueous. And so it's a solution, an aqueous solution. Benzoyl peroxide can be more pure. It's a solid. So less water. It's also soluble in organic solvents. No solvent is shown here. There's got to be a solvent there, most likely. I didn't show a solvent. You can also find benzoyl peroxide in the drugstore where? Or for what use? Yes, 10% benzoyl peroxide treatment of acne, yeah, because the peroxide will kill bacteria. Why? Because peroxides will homolytically cleave to make oxygen radicals, like bromine, okay? These guys over here don't like to bond to each other. It'll make radicals. All right, those radicals will kill bacteria. Those radicals will also promote here. It's like these radicals make this form radicals. It's another way and an alternative to light to get the bromine to become radicals. I'm not going to go into mechanistic details, but it's a radical initiator used in these reactions. Okay? Your textbook will probably give you more background on that. Basically, when you see either light or peroxide, you know you're doing radical reaction. Okay? So, basically we're doing a radical bromination. Where are you going to make radical at in this molecule? Same place you'd make cation. Where would you make carbocation? Benzoic carbon, yes, be stabilized by resonance. Okay? We're going to make, the bromine radical is going to take an H from that carbon to leave that radical. That is resonance stabilized. Okay? P orbital all the way around, and then that one in a P orbital. Okay? You can draw the pi system. Alright, you may not want to draw this if you don't want to use the ink over time. Sometimes it's better to listen. We've got one electron all the way around, pi bond, pi bond, pi bond, anywhere you want. But then we got a radical here. One electron, P orbital. And it's interacting with all the other P orbitals. And so the single electron in the P orbital interacting with the other P orbitals is more stable than if we put it out here. Put it out here, there'd be no P orbital here. That would remain CH2, tetrahedral. Okay, we can draw resonance structures. How do we do that? We've never done resonance structures of radicals. One of these electrons can come here and team up with that one. The other electron can come here. And that electron movement will give, what are we doing? We're teaming up between here to make pi bond here. And then the other pi electron went and is now sitting on the carbon. And we didn't do anything here. Yeah? One of these electrons can come here. This one can come here. So one of these and that one team up to make pi bond. The other one comes here. Moving arrows. We're using a fishhook arrow to move a single electron. We didn't do anything here. We made pi bond here. Single electron there now. And I can't draw a ring. And then you can move one electron here and make pi bond there and move the other electron here. You can do that one on your own. But when this reacts with bromine, it's going to brominate at the benzoic site. Okay? You got the mechanism there. This comes one electron here, the other electron there. Carbon-bromine bond here. The final product is benzoic bromination. Perhaps you're wondering, why does this not capture a bromine and end up with bromine here? If you made that product with bromine here, the ring would no longer be aromatic. And as we'll learn in organic 2, you're not going to destroy the aromatic ring unless it's a very vigorous reaction or unusual reaction. You're going to maintain the aromatic ring, and thus the bromination is going to occur at the original site, or at the benzoic. Benzoic bromination, a very common reaction. Regioselective. Radical bromination, making most stable radical, capturing the bromine in the propagation step. Okay, one below, NBS. NBS is N-bromosuccinimide. Now instead of bromine, BR, it's NBr. But with heat, energy, or something, this guy will homolytically cleave. And when it does, it'll produce Br radicals. It is a source of Br radicals, just like bromine is. There's some fine details here that we're not going to get into. There you go, source of Br radicals. Huge difference between these two. Highly toxic and corrosive. Not nearly as toxic or corrosive. This is a volatile liquid, meaning it gives off a lot of fumes and vapors, volatile, okay? This is a white solid. You drop bromine, you're going to have a mess, you're going to have to evacuate the lab. You drop NBS, you got a mess, you're going to have to find the broom and sweep it up. Which one would you rather use? Okay, it's a safer alternative. All right. Whenever you see NBS, it's bromine. It's a bromine substitute, bromine radicals. We got the light. This is a radical bromination. Okay. Where are we going to brominate this guy? Benzoic. Remember down. Where's the best place to make cation? Right there, yeah. Then we can do resonance. Okay. What's that position called? Allylic? Yes, allylic. Okay. It's going to take an H there, and we're going to get here. By the way, what takes the H is actually the N radical takes the H. And the fate of the NBS is you end up with this molecule, because it's what strips out the H. And that's just called succinimide. The N-bromo has been removed. It's just succinimide. This is going to capture the bromine radical. And we're going to end up with this product here. There's another possible product here because of resonance. Allylic bromination. What's another possible product? We do resonance here. This electron comes in here, teams up with one of those, and this one moves out here, and we get resonance arrow. What does that electron movement give? Here and here. Yeah? Well, this can capture a bromine radical. And that would give bromine there on the end. Of course, instead of taking it from bromine, you can take it from NBS. I'll just draw that like that. One of these electrons comes here, one comes here, one of these comes here. We make the N radical, and then the N radical can come back and strip an H out of another starting material, propagation. Now, that mechanism has some details which I'm just sort of making generic, because we don't need to get into the fine details there. But it's the same old. The only thing here is we're looking at resonance structure. Now, when we did resonance structure up here, I told you it's only going to react here. Because you're never going to, we drew other radicals, but you're never going to brominate at the other position because you would destroy the aromatic ring if you look at that product. But here, it's not, that's not important. You can actually, either resonance structure, you got to be careful, it's just one structure, right? The true structure is a blend of these two. Is a double bond here or here? Well, it's a blend. It's like this. And you got sort of, it's kind of a, it's hard to draw blends. You got sort of a radical here. What is it, a half electron? I don't, and you got sort of an electron here. But the other, the bromine, either this can take the bromine radical or this. Okay, it's easy to work with resonance structures. All right? Either one's possible. This is your other possible product coming from resonance, or considering resonance of the allylic radical to show the other allylic radical is conjugated. Resonance there. And actually, if you look on, I think, the front of the elimination handout, everybody got it handy? In blue. Actually doing this reaction here, 64 to 65, NBS, they're using AIBN. That is another radical initiator, similar to benzoyl peroxide, but it's something different. Similar role as benzoyl peroxide. Okay? It's a radical initiator. They're using carbon tetrachloride as a solvent. Okay? It's a radical bromination. Where's the best place to make radical out of this molecule? Yes, allylic. Possibly here, but it's substituted so it's more sterics. Probably up here. But why does the bromine not end up there? How do you get that product from that radical?
Resonance?
Now, there's resonance going on. And it actually is a delocalized radical, and it ends up capturing over there. Why? Well, that's an advanced consideration of why here. Also, they do give a yield, pretty darn good, 95%. Why is it so selective for this allylic site versus that allylic site? And that's some advanced consideration. I don't know that I could tell you. We'd have to look at it, have to look at conformations, et cetera, et cetera. But that's what they're doing there. There's some resonance involved. Why can't you use bromine in the last example? You actually cannot use bromine. You have to use NBS. Why come you can't use bromine? Brominate what?
Oh,
Yes, if we use bromine, you would end up brominating the alkene and getting a dibromide, a bisphenol dibromide from an addition reaction. That reaction is actually super fast. You see, bromine's not going to brominate an aromatic ring as easily. It can, we'll learn in organic too, but it requires a catalyst, not as easily. But bromine will readily dibrominate an alkene. We don't want that chemistry. So instead of using bromine, which can react two different ways, as shown above, we use NBS, and it's not going to do that chemistry like you did in lab with your hand behind your back. It's only going to do the radical. Okay? Because this is not electrophilic enough to do the bromonium ion mechanism. Okay, why is the ability to put a bromine on an alkane so important? We make this at the top. Is that the one we made at the top? Or if not, you can see this coming from. Is that? Yeah, we did make it at the top. Yeah, we made this. Why is it so important to be able to put bromine on a molecule, on an alkane? Because now you have a leaving group. And now with this substrate, we can do so many reactions, so many possibilities now. Where with alkanes, all you can do is burn them and do a radical bromination. Not much else. But the radical bromination allows you to hear, and now we can do reactions like we can treat this with potassium terbutoxide. What would that give? Maybe this alkene by a what? An E2 elimination. And I showed a Hoffman product. Possible. Now we enter alkenes. What else could we do? Convert what to an alcohol?
The alcohol halide. The alcohol E1 eliminate.
E1?
It's a tertiary substrate, right?
No, an E1 is going to give an alkene. SN1. SN1. Maybe take this, heat it with water. And be careful, if you heat too much, it's going to eliminate. We want a substitution, but we could get this alcohol possibly. No? Or we can make the same alcohol by making the alkene first and then reacting it with what?
Then you can react the alcohol with sodium and hydrogen.
Alkene. How can we convert it to this alcohol? Oh.
Using acids.
That's just H3O plus. You did that in lab. Or what? Or you can use oxymercuration followed by reduction. That'll give that product. Yeah. On the other hand, I'll come up here. What if we react that with BH3 followed by hydrogen peroxide and hydroxide? We're going to make the other alcohol, right? Antimercaptonic alcohol. What if we took this alcohol, reacted it with sodium metal, followed by benzoyl chloride? That bond right there, Williamson ether synthesis, yeah? Go on and on and on. Radical bromination gave us a substrate with a leaving group, and now we can do lots of organic chemistry. That's the power of the radical bromination. Ultimately, yeah? Where did this come from? How did we make that? We know how we make the put the leaving group on, radical bromination. Where did the alkane come from? the ground, from oil. Hydrocarbon, okay? Lots of hydrocarbon, and those hydrocarbons can be cracked. They can be converted to other hydrocarbons through thermolysis or whatnot. And most alkanes come from petroleum products, okay? And then you take something like that and you end up with something like this, or we can keep on and we can convert this into a drug that cures cancer or something through organic chemistry. Over here is drug synthesis using a radical bromination to make this breast cancer drug. '19 probably came from that, but look what they did from 19. Two leaving groups. Potassium cyanide, okay, SN2. Two SN2s kick off the leaving group, cyanide. From there, you can look at that reaction, but the next one, they take this product 21. What is this? That's right, benzoyl peroxide, NBS. What are we doing here? Radical benzoic bromination. Yeah? Now you have a leaving group. Then they come in with this nitrogen anion and kick it off, and then you got that bonded there, and that's the end product there. Kick off that leaving group. What do the leaving groups do? They're in the sun, they go bye, bye, bye. And that compound with that ring up there, that 3-nitrogen aromatic ring, breast cancer drug. You do have to be careful with these halogenated products, because you can put the halogen on by a radical reaction, but the halogen can also come off. Okay? Also come back off by a radical mechanism. And this is most important when it comes to the ozone, depleting the ozone layer. Halogenated compounds will deplete the ozone layer because of radical chemistry. Freon, which has been phased out because it causes damages to the ozone. With heat, sunlight up in the you-know-where, this can form radical, electron here, and we get, in this case, that radical plus Cl radical. And I'm broadening this out to any halogen, not just bromine. See, in our previous mechanism, when it captured the bromine radical to make the final product, well, that step is reversible. And this is reversing, because your carbon-halogen bonds, see, halogen doesn't like to bond. It likes to be by itself a little bit. It likes to form radicals. But then when you get these radicals, they can react with ozone, okay, O3, either one. So these can react or something. I'm not going to show any chemistry there, but when they react, you end up converting ozone to something else, and you're depleting the ozone. So Freon used to be used as a refrigerant, but now newer ones are made. Methyl bromide, methyl bromide is used to fumigate, but it's being phased out because it's a gas. It gets up in the stratosphere, etc. And this bromine is going to leave by a radical, and you're going to make CH3 radicals. Halogenated solvents. Well, tend to be some good solvents. They tend to be no toxic. They also tend to cause problems with the ozone layer and trying to phase them out. Like chloroform or dichloromethane, which you've actually used in lab. It's a real good solvent, but the ozone layer doesn't like it. All right? Because the carbon halogen bond goes the other way by the radical mechanism, goes back to radicals. Now, bond strength is important. Which makes the stronger bond to carbon? Which halogen makes the stronger bond? Or I can say, which makes the weaker bond to? What's the bond strength trend? Which halogen makes the weaker bond to carbon? You can look at the table I gave you. Iodine makes the weaker bond because it's so big, and also it's less electronegative. Okay. So the CCl bond is harder to break than a CBr bond. See, this bond is easier to break than that because this carbon-bromine bond is weaker. Carbon iodine is even weaker and even easier to break. Doesn't take as much heat or light. Okay, there's a couple of mechanisms down here to sort of use as practice. But the idea that the halogen can essentially, hey, it's leaving, right? But it's leaving by not an ionization, right? Because if something like this or chlorine did this, it's going to make ion, right? But if it leaves instead like this, that is, one electron goes to the bromine, the other one here, you're going to make bromine radical plus carbon radical. I don't think you want to call that ionization, because I don't see any ions. They're both neutral. So you've got to be careful not to call it ionization. But I reckon the bromine is leaving. So it looks like bromine can leave by ionizing, but it can also leave by this radical mechanism. Yeah? Or chlorine. But if you try a couple of mechanisms here, everything will fall together if you just kind of look at it and see what you need to do. Of course, this has one carbon and that has two, so it looks like you're going to have to use two of these. You want to balance this? 8 and... Well, that's not balanced, because now I got 8 chlorines and 6 chlorines. But I got the right number of carbons. I don't know, you can balance it. What I know is that if you take carbon 10 and heat it, you can get this. The chemistry doesn't... I'm sure there's multiple molecules there. But one of these reactions, you ever heard of Michael Faraday? Did a lot of physics. Yeah, talk about Faraday in physics? Yeah. Faraday's law. He was also an organic chemist. So next time you talk about Faraday, make sure you say, hey, he was a chemist, right? But Faraday actually discovered this reaction here, as I noted up there. Okay, one last thing. Different reaction here, although it's still radical. Let's turn to alkenes. Okay. Of course, review. We can hydrate an alkene, Markovnikov, or we can anti-Markovnikov, right? We just did a little review of that 10 minutes ago. But what about HBr? If we react the alkene with HBr, we're going to get this product, right? And we can call that a Markovnikov hydrobromination. Markovnikov meaning to me, and what I tried to get you to think about is, it's sort of a standard reaction based on where you're going to form carbocation. Where are you going to make carbocation, left or right?
Left.
Left. And then the bromide adds to the cation. That's why bromide or bromine is now there. Okay? Standard Markovnikov. Well, how can you get bromine on the other carbon? Like we did over here. We were able to hydrate and get alcohol on the other carbon. Can you do this and get bromine on the other carbon? Well, the answer is yes. And I typically do not cover this reaction during test 2 material. But it actually was on that puzzle. And a couple of you asked about it. Like, what is this? Did we cover this? I said, no, we'll cover it at the very end of the course. Okay? Well, it turns out you can do this anti-Markovnikov if you take HBr, but put in a peroxide. And you can use hydrogen peroxide here. If you put in peroxide, it will reverse the regiochemistry and give you the anti-Markovnikov product. All right. Is that good enough for you, or you want to see mechanism?
How?
How?
Yes.
How? Good. You should always want to see mechanism because chemistry is not magic. Well, what do you think the peroxide does? Peroxide is a radical initiator. Okay? We don't have Br2, we got HBr. Well, the HBr can also do the radical. You know, we just did carbon halogen, making radicals. This can also do radical. And instead of ionizing to make H plus Br minus, we can do radical. That is, we're going to do homolytic bond cleavage as opposed to heterolytic. Heterolytic lead to ionization. And again, the peroxide promotes this. I'm not going to show how that does, but okay. Peroxide promotes this. All right. Now this reaction is sort of got a lot of details where you're going to ask how many times and why. We don't have enough time because we only got 5 minutes left. Okay? How, why? But this reacts with the bromine radical. Because typically it reacts with H plus, right? And it reacted and put H here and cation here. We don't have H plus. We got H radical. But here it reacts with bromine radical. Okay? One electron here, the other electron here. Those team up. Because where are you going to make radical at? Right or left? Same place, cation. But in this case, we made bond to bromine. And we left radical here. Now you could ask, well, why doesn't this capture H radical and put H here? And I told you, you would be asking why? Why? We're not going to do that because we only got a couple minutes left. You can read about it. I'm trying to give you more than just magic. And then this, then you propagate. You don't capture the H radical or you'd be dead over there. Instead, this comes in here. You make the carbon H bond and you make bromine radical again, and then it can come over here and repeat. In the end, this reaction is convoluted. There's too many Y's, and this is one reason I don't cover it during test 2. In the end, to me, this is one where you can just consider it magic. Okay? Here you go. If you have your standard alkene reaction with HBr, you know what the product is, right? What do you get if you put peroxides in there? Reverse regiochemistry. All right? right? And I'm fine with you just, because otherwise it's, okay, for us at this point. Here's the problem with this, and we're out of time. You can't confuse the previous chemistry we did in this handout with this reaction. The previous chemistry was alkanes. The only time you react the alkene is with HBr. Now you can't react alkene with Br2, but that's the old behind your back mechanism. Br2 radical is always alkane. HBr radical is this reaction. Don't confuse them. This chemistry will be on final exam. If you have questions, let me know. I'll let you know about review on Monday at 2:30. There we can have that at. One last thing, guys.